Hello guys, so this is the my own review of chapter 14 of orthogonality. So um, I will discuss these two topics, these two takeaways from the chapter that I think is really useful. So the first one is some proof that the Pythagoras theorem is actually proving that agreeing with our two vectors, orthogonal vectors are zero. So here is the Pythagoras theorem that says that if you have this is side of x and side of y, and this is the right triangle with this right angle, and this is will be equal to this equation basically, so x plus y equal 2. So you can check like quickly, like 3 squared 9 plus 4 squared, for example, um, and this will be equal to 5 squared. And let's connect this theory to the linear algebra. So in linear algebra we are interested in the vector world, so that's why we need to add this notation here, which means the length of vector. So this is the length squared. So this is the length squared. I will discuss about this in more details in other videos. Length squared, okay. And this will translate to the x transpose x plus y transpose y equal to x plus y transpose x plus y. And let's expand this term. So you have x transpose x and then plus x transpose y plus y transpose x plus y transpose y. Cool. So you have so this term will cancel out. They're the same thing. So you have two. So these two are the same thing because x transpose y. This is just dot product of these two, and this all dot product of these two. So let's do this, and this will equal 0. So this I think this is kind of beautiful because it connects the theorem that we know already exists so far, the famous Pythagoras theorem, and the theory that we will discuss in this chapter, which is the orthogonality, that two orthogonal vectors will be 0. Okay. And now, so this one is covered. I already deleted those quick proof. And let's discuss the second one. I will begin with the example from the lecture, which is quite insightful, I think. So Professor Strang has this example where he draws this, like the floor of the class as a subspace W. Let's name it W, and then other subspace in this the floor against it, the place where he puts the whiteboard and stuff. Here, name it as V. So in a glance, quickly, these two subspace seems like they're orthogonal, right? Because these two create the right triangle there. But it's not, because the definition of the two subspaces being orthogonal is that all the vectors in W, like all the vectors, I will put an emphasis on as there. So this means all the combinations of those vectors, because again we are talking about subspaces here, and we are talking about spaces, we mean the combination of all the vectors inside. So clearly, like, this one is not orthogonal to this one, or even like, yeah, this smaller one doesn't orthogonal to this one. And even more, there are vector that exist in both subspaces, which is this one right here. And clearly, like, these vectors are not orthogonal to itself, because you cannot be orthogonal to itself. So this covers the first chapter, I mean the first point here. And let's move on to the second and third. I kind of want to discuss them simultaneously. So we know from the previous chapter about the column vector and how to compute the left null space. So we have this ax equals 0. And let's give a concrete one example. Let's say we live in R3. let's create a random vector 1 2 3 and 1 to 1, and then a third redundant one will be to add up these two, so 2 4 4. Okay, so this is clearly linear dependent vectors because you can create this out of the combination of vector 1 and vector 2. And then there's the null space of x, so the solution of x is the null space, and this will be 0. Okay, so what I'm doing here essentially is this. If you notice, what we have been doing so far is we're computing the dot product of this row vector to this one, and then the second one to this one, which means we're computing all the possible combination of this one, and we dot product with this vector, and we want them to be 0. So what are we doing here? As essentially we're saying that this row vectors, the combination of row or the row space of A is actually perpendicular to this solution here x, so perpendicular to the null space of A. And consequently, we also know that the column space, with the same logic and whatever, the row space of the column space of A is perpendicular to the left null space. So in terms of the notation, this will be RA, and this will be the null space of A, and this will be the CA, and this will be the null space of A transpose. Okay, cool. So we cover this one, and then let's talk about the dimension here. The dimension, as we also know from the previous chapter, that this matrix A have the dimension of R, while the dimension of the null space have the dimensions of n minus R, and then they add up to the whole dimension, right? So in this case, we know that we create some redundant factor here, so we know the R is 2 and the n minus R is 1, so I should create this more beautifully. So R plus an R must be 3. So this is what we got. So we know the 2 plus 1 equal to the dimension of the whole space, which is the R3. So 2 plus 1 equal 3. Cool. So this cover this one. So it's saying that for this to happen as well, for these two subspaces to be orthogonal, so the dimension must also add up. So in this case, the row space of A plus the dimension of n space must be 3. And I will introduce quickly some term that is discussed in the book and introduced as well. So this term right here being called the orthogonal complement. Nice. So next I will discuss some examples that I think is important just to get this concept into our head. Now let's see some example that I think is quite teasing your brain a little bit just to get the concept right. So the first one, I have two lines that is creating the right angle in R3. So is this orthogonal? Well, the answer is no, because we know previously the dimension should add up. So this one, the dimension doesn't add up, so it is only one subspace, dimension 1 of the subspace, and this also has a dimension of 1, so 1 plus 1 doesn't equal to 3. And what about the second one? So right now we live in the two dimensions, the R2, and we have these two subspaces creating the right angle. And what do we say? In this case, yes, the dimension add up. But I would also want to mention that it's important that they are intersecting at 0.0. They intersect at 0.0. Because if they don't, let's say this is just a random point like 1.2, then these two are not subspaces to begin with, so it doesn't matter if we consider the orthogonalities. So make sure that this is also an important thing that you should not forget. And we move on to the third example here. So this is also a quick example from the book. We live in R3 and we have these subspaces of a line, and this is, we want to say this is through the origin of the dimension 1, and we have this space of green spaces that is in the dimension of 2. And is it orthogonal? The answer is yes, because we can see also like visually, geometrically, this vector, all kind of vector that live here, is orthogonal to all the vectors that live here. They are creating the right angle, plus including also the 0 vector. So they are orthogonal. What about the second one? Well, this is kind of one example that I kind of thinking when I see this. So here what I confused about at first is that the dimension add up to 3, so 1, 2, 3. And okay, clearly from the geometrically it does not look like they are orthogonal, because you can see if I have a vector here and this one is clearly in the same direction as this one, they are not orthogonal. But so does that mean that this rule, that the dimension being 3, all of them add up to 1, does that, it's kind of violating what I defined earlier, that the dimension must be equal to the whole space of dimension in order to be orthogonal. So what happened here, I wonder? The dimension add up to 3, but they're not orthogonal. Okay, so another thing to look at is that in these subspaces, it doesn't go through the origin. It doesn't have a point. It doesn't go through 0. So it's not a subspace to begin with. So in this case, yep, it's not orthogonal. Of course, it's not a subspace. So we don't even need to consider about it. Okay, that's it for my review of chapter 14. Thank you so much for listening. Bye bye.